So now we're going to prepare our FMOs for feature engineering. So as I described in the last video, FMOs are often used in manual gating to control for data spread and spillover. So we're going to start by cleaning up the data by renaming the columns to the names of the markers rather than the floors. So here we're taking our FMO gated data. So this is the data, remember, that we've converted to a data frame here. And we're only going to keep the fluorescent markers that end with -A. So this is removing a lot of the height parameters that we're often not interested in. And we don't need our forward scatter anymore. So we basically just want to keep all of our fluorescent markers and our file name and our side scatter. So first we're going to rename each of the individual floors to the specific marker. So this will just make it a little bit easier to understand all of our results here. So we're using the rename function here to change the name of the columns. This NA omit is going to omit any rows that have any NAs in them. Here we're going to be filtering to where the side scatter isn't the maximum side scatter value. So this is removing any data that is on the very, very edge of what we want to be seeing. And then one of the really important things for the package right now is that all the FMO file names need to exactly match the names of the column markers. So for example, if the file name says CD103_F, but the corresponding column name says CD103, you need to either change the file name or the column name so that they are exactly the same. So this is what I'm doing right here with the mutates for interferon gamma. First off, in this data here, we can see that all the file names have .fcs. And so right here, I'm using stringer replace. And for the file name column, anything where it says .fcs is going to be changed to nothing here. And again, in our file name column, we have ifng as the file name that's listed here, but we want it to say ifn because that's what matches in our column name right here. So those have to match exactly. And then here with our filter _FMO, we're going to take this data frame of our FMO gated data and filter it so that we have all of the file names that match up with the marker. So this is a snapshot of what the data looks like here. So the file IL10, we're only saving data for the marker IL10. So traditionally, FMOs have been manually gated to identify the upper threshold of a parameter's value for negative cells. In our pipeline, we automate the analysis of the FMOs, measuring the threshold as the 99th percentile of the parameter values in each FMO. We're using this 99th percentile, as I said in the first video, because we can have some noise, and so this is just accounting for a little bit of the noise. So we use this get 99 on our FMO filter data, and so this finds that 99th percentile that we can see here in our add quantile object. So we have each of our different files, so CD103, CD122, each of these FMOs, and where that threshold is going to be placed with our quantile 99 here. Then we can assess this 99% threshold with FMO plots and make sure that each of the FMOs has been properly read in. So we can see this is where our threshold is going to be. These are each of our different FMOs. Just of note, you can see here with the CD69 that it's a lot more spread out, and so it might be indicative of spillover. So I'm actually going to remove this marker from the analysis for that reason. And just a note, if you don't see all the FMOs that you want to use, it's probably because the names didn't exactly match up when you were doing your data frame FMO gated data here. So just go back and make sure that anything that's listed in the file name column exactly matches with the column names. So now that we've analyzed our FMO data, we're going to go back through and look at our actual sample data. And so this is doing the exact same initial gating that we did with our FMOs here, where we're navigating to our sample folder, we're reading in the data as an NCDF flow set, we're gating with the exact same gating strategy. We can view the gating with this auto plot function. And for example, you can see here, it might be a little bit difficult to see the gating for the live cells here. So this is just an additional way to visualize some of the gates with the ggcyto package. And so this is a little bit easier to see our live gating here. And so again, this is just pulling out the first sample in our gating strategy. We're looking at our zombie NIR on our x-axis. We're showing a density plot with our geome area. And we want to show our live gate that matches with our zombie NIR. With the ggcyto set, we can set the limits of our y and x axes. So on the y-axis, we want to go from 0 to 2 times 10 to the negative 4th, as we're showing here. On our x-axis, negative 1,000 to 1 times 10 to the 5th. And then this is just making the plot a little prettier by labeling our x-axis and our y-axis and the title of our plot. Geome stats, this is giving where we want to put the statistics on our plot. And then this is just changing the size of the axis text, the title, etc. And again, this is the same thing that we were doing before, where we're taking out our live population, converting the cyto set to a flow set, and then into a tidy data frame. And then here with this unique function, we can look at all of the different samples and make sure that they're read in properly by looking at our data frame all gated, looking at the column file name, and seeing all the unique ones. And again, this is a snapshot now. We have our data frame all gated, and it's the exact same as I showed before at the FMOs, where we have our files here. Each row is a different cell, and each of the columns is a different measurement that we read on the flow cytometer. And again, we're going to clean up the data a little bit here. So we're taking our data frame all gated, and this isn't completely necessary, but this makes the analysis later a lot easier. But in our file name, you'll notice that we have information about our time point, the organ, the group, and what number the animal was within the group. And so here I'm pulling out all of the information into different columns. So the time point, I'm pulling out anywhere where it says D and then a bunch of numbers. That's going to be the time point. So this is pulling out day 30. And then for the group, I'm extracting anything where it says group, punctuation, so that underscore that we see up here, a number, underscore again, and then a letter A through Z. And then the stringer replace that I used before, this group underscore, anywhere where it says group underscore, I'm going to replace it with nothing. And then to clean it up a little bit, I'm going to rename the file name by uniting the column time point and group. And so the time point in group is then going to be called, the files will be day 31A. So it's removing some of that extra language. Again, doing the same thing that we did above with the FMOs by selecting only those with the area and renaming these to the correct marker name. And so this is what the data looks like. It's the same as the FMOs, where we have all of our different markers that we're interested in, and then we have our file name as well. So now we're going to feature engineer our data. And so feature engineering is a technique that uses original features in a data set to create new features that make the data a little bit easier to understand. So I described this in the first video, but we're going to be converting all of these continuous values that we see here into binary data, zeros and ones, where 0 is going to be negative for a marker and 1 is going to be positive for a marker. And so we use this FE function and all of our data from our add quantile. So that's the data frame that contains information about where the threshold should be placed. And then we're going to apply this for each of our different columns. So this is applying that 99th threshold and feature engineering it so that it's all going to be zeros and ones, as we can see in this plot here. The count calc function at the end calculates the cell counts and percentage of cells in each sample for each population. And the data frame that's input into this function should only contain the markers that we're interested in looking at. So we have to remove things like our side scatter. If you still have forward scatter, we want to remove our live because we've already gated on our live cells initially. And in this case, I also removed FOXP3 and CD69 because we had spillover in those channels. And so the data wasn't really looking good here. And so here in our resulting all FE data frame, each row is a different cell phenotype. So that's defined by a combination of positive and negative expression. So for example, here, this first cell type is negative for every marker except for SCA1. So we have lots of different combinations of zeros and ones to create different cells. And so here we have the file name. So in our day 31A, we have the cell type that's negative for every marker except for SCA1. There are 15,000 cells that have this phenotype out of the total 76,000 cells within this file. And so 19% of cells express this phenotype here, for example. So I've also added this additional function, check FlowJo, which is an optional check if you want to confirm the feature engineered results with manual gating in FlowJo. So it can be used to calculate the percentage of cells in each sample that express a specific marker. So for example, if you were doing a side-by-side manual analysis for CD3, you could say I want to check with FlowJo. So we put in our allFE object here. We want to look at CD3. And so this is saying in our file, day 31A, 17% of cells express CD3. In day 62A, we have 18% of cells expressing CD3. And so if you want to go and do a manual check, this just shows the percentages that you should be seeing for the different markers. So be sure to check out the next video, cytotypr visualizations, where I'll show how to visualize all these different cell populations.